So we are now leaving finance, and we're going to begin a short study of probability and statistics. So we start with this video on probability. Here's the outline. We have to spend a little bit of time talking about sets, and then we'll look at the basic idea of probability, and then the details, and then the bulk of the remainder of the video will be spent on theoretical probability. So beginning with sets, sometimes if we have a collection of objects, we think of the collection itself as being an object. For example, we might talk about a set of silverware and think of the set of silverware as being an object. So when we want to think of a collection of objects in this way, the language of set theory is handy. So here's how that works. The word set in mathematics, means a collection of objects. Pretty much the same as its ordinary English meaning. You can describe a set in words, or you can describe it symbolically by enclosing the objects in a set of braces. So, for example, the set containing the numbers 1, 2, and 3 could also be written by listing the objects in the set 1, 2, and 3 between these left and right braces. The word subset, if S is a set, A is a subset of S, means that either A is equal to S or that you get A from S by deleting one or more of the objects in S. So this means A is a subset of S, means that either A is equal to S or A is a smaller set. So, for example, the set consisting of the objects 1 and 3 is a subset of the set containing the objects 1, 2, and 3. You get this set 1, 3 from this set 1, 2, 3 by deleting 2. And 1, 2, 3 is a subset of 1, 2, 3. Every set is a subset of itself. A set S is a proper subset. That is to say, if S is a set, a proper subset of S is any set you get from S by really deleting one or more elements. So, for example, the set containing the objects 1 and 2 is a proper subset of the objects 1, 2, 3, of the set containing the objects 1, 2, 3, because you get this first set 1, 2 from this second set by deleting 3. But 1, 2, 3 is not a proper subset of 1, 2, 3. A set is not a proper subset of itself. And finally, the last phrase in the language of set theory, if S is a set and little a is one of the objects in S, we say that little a is an element of S. So the phrase is an element of and the phrase is an object in have the same meaning. There's shorthand notation for all of these concepts. A is a subset of S. The shorthand notation is this capital A sideways U with a little horizontal bar underneath S. So this is read A is a subset of S. Just a shorthand for the longer English phrase. So for example, if we wrote the set whose elements are 1 and 3 is a subset of the set whose elements are 1, 2, and 3, that would be true. And similarly, the set whose elements are 1, 2, and 3 is a subset of itself. The notation for proper subset, capital A is a proper subset of S, is almost like the subset notation. It's just that the little horizontal bar underneath the sideways U is missing. So the statement, the set whose elements are 1 and 3 is a proper subset of the set whose elements are 1, 2, and 3 is true. But the statement, the set whose elements are 1, 2, and 3 is a proper subset of itself is not true. The shorthand notation for little a is an element of S. Right? Remember, this means that little a is one of the objects in S. Is this the symbol for is an element of looks like a Greek epsilon, but this is read little a is an element of capital S. So for example, the number 2 is an element of the set whose elements are 1, 2, and 3. But the set whose elements are 1 and 2 is not an element of the set whose elements are 1, 2, and 3. Right? The only objects that are elements of this set are the numbers 1, 2, and 3. So we'll find that both of our textbooks use the proper subset notation much more than the subset notation. Okay, one more abbreviation. If capital S is any set, we use N followed by S in parentheses to mean the number of elements in S. So this is read N of S, and what it means is it's shorthand for the number of elements in the set S. A quick example, the number of elements in the set whose elements are 1, 2, and 7 is 3, because the set has 3 elements. And now a few more examples. Here's a set described by listing the objects in the set between braces. I called it capital S. So the elements of S are 3, 5, 7, 11, and 13. Just the objects that appear in the list between the braces. The number of elements in S is 5, because S has 5 elements. So N of S is 5. Here are some sample questions, further examples. What is N of the set 2, 4, 6, 8, 10, and 12? In other words, we're asking how many elements are there in this set. A quick count shows us that there are 6. Is 4 an element of this set? 2, 4, 6, 8, 10, 12. In symbolic notation, we would be asking it this way. 4 is an element of 2, 4, 6, 8, 10. True or false? And this is a true, because 4 is one of the objects that appears in the list. And finally, is the set whose elements are 2 and 10 a subset of this set shown on the right, 2, 4, 6, 8, 10, 12? And the answer is yes. 210 is a smaller set. In other words, 210 can be obtained from this set on the right by deleting all the elements other than 2 and 10. So if you have a set described by listing its elements, here's an example. It may be hard to describe the set in words. You may not be able to find a nice description, but one possibility in this example would be to simply say that capital A is the set with elements 1, 5, and 11. It's a lot longer than just listing the elements, but it is a way of saying it in words. We may be able to find a nicer description looking at the set whose elements are 2, 4, 6, 8, and 10. We could describe this as the set of even numbers between 2 and 10, including 2 and 10. It's not a very short description, but it is a description in words. So the main thing we'll be doing in our study of probability is counting the elements of a set. And usually having the elements listed makes this easier. Okay, so let's try one more example of counting the number of elements in a set. So I'm going to use capital J to be the set whose elements are the jacks from an ordinary deck of playing cards, an ordinary 52-card deck. So I would like to know what is n of capital J. What is the number of elements in capital J? You probably already know, especially if you're familiar with playing cards. So we'll be looking at the question, what is the number of elements in capital J? But if you're not familiar with playing cards, I'm going to take just a brief minute here to describe an ordinary 52-card deck. Okay, here is a picture of an ordinary 52-card deck. Ignore these three cards in the bottom row. So there are four suits. The suits are called clubs. Those are the cards in the first row of the picture. There's a suit called diamonds. Those are the cards in the second row. The heart suit is the third row, and the spade suit is the fourth row. And in each suit are cards. You have the cards ace, 2 through 10, jack, queen, and king. So on the next slide, I've put on the slide what I just said in words. There are four suits. There are four suits. Clubs, this is the symbol for clubs. Diamonds, this is the ordinary symbol for the diamond suit. Hearts, and spades. So they're represented by the four rows of the picture we just looked at. And rather than try drawing these symbols for the four suits, we'll simply use C for clubs, D for diamonds, H for hearts, and S for spades when we're talking about a deck of cards. And as I said when we were looking at the picture of the deck, there are 13 cards in each suit. There is an ace, there are cards 2 through 10, there's a jack, there's a queen, and there's a king. And we'll use A for ace, 2 through 10, and the symbols J, Q, and K for Jack, Queen, and King when we're talking about these playing card examples. So back to the original question. If J is the set of jacks from an ordinary 52-card deck, what is the number of elements in the set J? 4. As we saw, there are 4 jacks in an ordinary deck, one from each of the 4 suits. Okay, now there are 2 operations on sets that we want to look at, which will be useful in our study of probability. So assume we have 2 sets, and just so that we have an example to look at, I'm using A being the set whose elements are 1, 2, and 3, and B in my example is the set whose elements are 2, 5, and 7. Okay, the first operation is known as the union. The union of 2 sets. And roughly speaking, what this means is you put the 2 sets together to make one big set. The shorthand for the union is this A, what looks like a U, B. And the description is it's a set of all objects which are either in A or in B or in both A and B. So in this example, the union would have to contain all the numbers in A and all the numbers in B, including the number 2, which is in both sets. So A union B is the set whose objects are 1, 2, 3, 5, and 7. And we only list the 2 one time. The other operation is called intersection. And roughly speaking, this is the overlap, this is where the 2 sets overlap. The intersection of A and B. The short notation, the shorthand notation, is this A upside down U, B. A intersect B. And the description is, the precise description, it's all objects which are both in A and in B. So if we look back at our example, we would be looking for objects that are both in A and in B. And there's only one, right? The number 2 is the only object that appears in both sets. So A intersect B is the set containing just one object, namely 2. Okay, so now we are moving from sets to probability, and we'll start out with an example which we will come back to later. So let's say that you roll a 6-sided die with faces numbered 1 through 6. So a die is half of a pair of dice, right? It's a cube, and the 6 faces of the cube are numbered 1 through 6. And a typical probability question would be, what is the probability of rolling a 2? So we'll come back to the question later. But on this slide, I just want to tell you a few things about probabilities. So probabilities are assigned to events. Like rolling a 2 is an event if you're rolling a 6-sided die. The probability of an event is supposed to be the fraction of the time that event will happen. Probabilities are expressed as fractions between 0 and 1, or as decimals between 0 and 1. So you find a probability 0.5 say, for some event. That could be expressed either as a fraction 1/2, or as a decimal 0.5, or as a percent. 0.5 is 50%. But in this course, we will mainly be using fractions and decimals. If an event is impossible, its probability is 0. If it's sure to happen, its probability is 1, or 100%. And all other events have probability somewhere between 0 and 1. Or between 0% and 100%. So here are some of the details of exactly what probability is. So we're going to suppose that we have a repeatable experiment, like rolling a die with faces numbered 1 through 6. You're planning to do this experiment and observe some aspect of the result. So if you're rolling a 6-sided die with faces numbered 1 through 6, the natural thing to do would be to observe the number on the upward face. If you look at all possible values for the thing you're observing, that set is called the sample space. And usually when we're talking about sample spaces, we will denote the sample space by a capital S if we want a single letter abbreviation. So in the example of rolling a 6-sided die with faces numbered 1 through 6, the possible outcomes for the number on the face-up side are the numbers 1, 2, 3, 4, 5, and 6. So those numbers form the sample space in our example. And an event is a subset of the sample space. Events are frequently described in words, but they can also be written using the set notation by listing the objects in the set between braces. So a few examples of events. I'm going to let E sub 1 be the event that the number rolled is an even number. If I wrote that using the set notation, listed the elements between braces, it would be the set 2, 4, and 6. Because of the 6 possible numbers you can roll, 2, 4, and 6 are the even ones. And here's takes us back to the set theory part of the presentation. The number of elements in the set E1 is 3. Let's try let E2 be the event that the number rolled is 3. So writing this using the set notation, it would be the set containing just one of the possible outcomes, namely 3. This is so obvious it might be slightly confusing. And what is the number of elements in this second event, E2? There's just one. And as a third example, E3 is going to be the event that the number rolled is smaller than 6. What does this look like as a subset of the sample space? The numbers 1, 2, 3, 4, and 5 are the outcomes that are smaller than 6. And the number of elements in this event is a 5. So what we want to do is assign probabilities to the elements of a sample space. And once we do that, that will give us a probability model for the experiment that we're performing. So the probability of an outcome, probability of something in the sample space, is supposed to be the fraction of the time that outcome will occur if the experiment is repeated a large number of times. So in our example, we're going to assume that the die that we're rolling is a fair die. In other words, we're going to be assuming that all 6 possible outcomes are equally likely. So we would expect each of those outcomes to happen 1/6 of the time. And so we would assign a probability of 1/6 to each of those 6 outcomes. And we could express that probability model as a table like this. We list the 6 outcomes in the top row, 1, 2, 3, 4, 5, and 6, and we list the probability of each outcome below the outcome. So in this particular probability model, each outcome has probability 1/6. And then to get the probability of an event, so here's some notation that's used in both of our textbooks. If E is an event, then capital P of E, that's P followed by capital E in parentheses, is shorthand for the probability of the event E. So in any particular example, this will be a number. Between 0 and 1, as we've seen. So to get the probability of an event, you can add the probabilities of the outcomes that are in that event. So for example, if you wanted the probability that the number rolled is even, that's the probability in set form. The outcomes 2, 4, and 6. 2 has probability 1/6, 4 has probability 1/6, and 6 has probability 1/6. Adding those up gives you 3/6 or a half. So the probability of rolling an even number in our example is 1/2. In general, if we do an experiment like rolling a die with a sample space capital S, and if we know the number of elements in capital S, that's n of capital S, and if the outcomes are all equally likely, and if E is an event, and we know the number of things in the event E, then the probability of E, the probability that E will happen, is the number of outcomes in E divided by the total number of outcomes in the sample space. So it's the number of outcomes where E happens divided by the total number of possible outcomes. So this is a way of finding probabilities when you're talking about an experiment where all the outcomes are equally likely. So let's try a few examples. So what's the probability that the number rolled is even? Thinking of probabilities in the way described in the previous slide. Well, you roll an even number in 3 out of the 6 possible outcomes. The probability that the number rolled is even is 3/6. This paragraph is a longer description of what I just said. What's the probability that the number rolled is a 3? Well, a 3 is rolled in only 1 out of the 6 possible outcomes. The probability of rolling a 3 is 1/6. What's the probability that the number rolled is smaller than 6? As we saw, you roll a number smaller than 6, in 5 of the 6 possible outcomes. The probability of rolling a number smaller than 6 is 5/6. Okay, switching examples. Let's suppose you have a coin that you're going to flip twice. So we'll have a first flip and a second flip, and we're observing whether you flip heads or tails on your 2 flips. So what would the sample space look like if you're flipping a coin 2 times? Well, one possibility is that you flip heads and then heads. That's abbreviated here by HH. HT means heads first and then tails. TH means tails first and then heads. And TT is short for tails and then tails on both flips. So here's another sample space. Seems reasonable to assume that all of these outcomes are equally likely. Each of the 4 outcomes is equally likely. So the probability model, expressed as a table, in the probability model we would assign a probability 1/4 to each of the 4 possible outcomes, assuming that they are all equally likely. Okay, so a few probability questions. In this situation, what's the probability that both flips are heads? That happens only in 1 of the 4 possible outcomes, namely the first, heads. So the probability of flipping heads twice in a row is 1/4. What's the probability that both flips are the same? Let's see, that happens in 2 of the 4 possible outcomes. Right? Both flips are the same if you flip heads or if you flip tails. So the probability is 2/4. In reduced form, that's a half. And what is the probability that both flips are different? Well, this also happens in 2 of the 4 possible outcomes. The flips are different if you flip heads tails or tails heads. So the probability is 2/4, or 1/2. And now a third example, back to the deck of cards. So now we're drawing a card from an ordinary 52 card deck. So we're going to assume that every card has an equal chance of being drawn. Sometimes we express that by saying the card is drawn randomly from the deck. So every card has an equal chance of being drawn. Here's a picture of the deck again. Ignore this bottom row again. Okay, so we'll have to keep this in mind as we try to answer these probability questions. What's the probability that the card is the 9 of hearts? Well, out of the 52 possibilities, only 1 is the 9 of hearts. The probability is 1/52. What is the probability that the card is a king? Out of the 52 possible choices for a card, 4 are kings, so the probability is 4/52, which in reduced form is 1/13. And what's the probability that the card is a heart? 13 of the 52 cards are hearts, so the probability of getting a heart is 13/52, or 1/4. Okay, one more example. Well, actually, there are 2 more examples, but we have a jar containing 9 red balls, 10 blue balls, and 4 green balls, and we're going to select a ball randomly from the jar. So each ball has an equal chance of being chosen, but what we're going to note in this case is the color. The sample space is going to be the colors red, blue, and green. So here's the beginning of the probability model in table form. In the top row I have the outcomes, red, blue, and green listed, and now I would like to fill in the probabilities. Well, there are a total of 9 plus 10 plus 4, 23 balls, and 9 of those are red. So the probability of getting a red ball is 9/23. 10 of the 23 balls are blue. Getting a blue ball has probability 10/23, and 4 of the 23 possible outcomes are green balls, so a green ball has probability 4/23. And now let's look at the probability that, before we do, we want to make sure that the probabilities in our probability model add up to 1. So what is the probability that the ball drawn is either red or green? I'm going back to the table for just a minute. You get a red or green ball in 9 plus 4 and 13 of the 23 possible outcomes. So of the 23 balls, 13 are red or green, so the probability is 13/23. Okay, and our final example. So we have a test that was given to a group of 65 students, and the results of the test are summarized in this table. So in the second row are listed the grades for females in the class, right? 10 A's, 4 B's, and 12 C's. A total of 26 female students. In the second row are the grades for male students: 8 A's, 18 B's, and 13 C's, for a total of 39 male students in the class. So 26 plus 39 is 65. That's the total size of the class. And in the columns, you see how the grades are distributed, right? For the A's, 10 A's were earned by female students, 8 by male students, for a total of 18 A's. And similarly for B's and C's. Okay, and now we're going to assume that a student is chosen randomly from this group. In other words, each of the 65 students has an equal chance of being chosen. And we're going to try some of the probabilities. So what is the probability that the student was male and got an A? There were 8 male students that got A's. Of the 65 outcomes, the student was male and got an A in 8. The probability of getting an A should be 8/65. What's the probability that the student was female? Well, here, at the right-hand end of the second row is the total number of female students. Of the 65 students, 26 were female. So the probability of getting a female student is 26/65. And finally, what's the probability that the student selected did not get an A? The students that did not get an A are the 22 Bs and the 25 Cs. There are a total of 47 students who did not get an A. The probability of not getting an A is 22 plus 25 over 65, or 47/65. So there are a couple of more slides in this slide presentation, but I think we'll stop the video here.